Okay. Test 1 2. Test 1 2. Okay, seems reasonably loud enough. Well, we confirmed that we didn't fuck up anything else.
we present Saturn.
Talking. Can you hear me okay? Oh, hey. Prabal had to remind me that you were, oh, that's right.
I delivered her to the top.
I don't want to be rude, but I'm going to leave before 5 o'clock, so.
That's fine. I'll leave too.
It's not because, you know.
That's fine. No, but as you're on your way out, just stomp your feet and go, it's garbage.
Oh, it's going to be cool.
I'm Florence.
Oh, okay, great. Okay, perfect.
Nice to meet you.
Good to see you. Well, for you, not for me.
Well, initially, I was planning to come on Monday. I'll give him a call.
Yeah, no, good timing, exactly. Yeah, we're super excited to have Gregory. Yeah, likewise. Good to see your citizens over. Okay, go. Yes. What?
Oh, is this for me?
Yes.
Excellent. Is this a stop talk button?
It's a, what is it called? A catch box you throw it to whoever wants to ask a question.
How did it go with John?
Great, yeah. Just getting bombarded by text by my assistant about things I need to do today. Yeah.
See, it's context aware.
He knows you have a little moment of put on my glasses.
I know.
So we'll probably go, I don't know how much like close to an hour, but I want to give you time for Q&A.
Yeah, so I'm going to need to cut off at some point, but I'll do that and try to.
We have the
Okay.
room. We won't be booted out.
Yeah, no, but it's much more interesting to respond to questions than me to just blather on.
Right.
Yeah, I had to buy a pair of reading glasses this morning because I broke all my glasses in the last couple months, so I'm relying on these reading glasses. should be okay on battery.
All right. Welcome, everybody. I know it's the end of the semester, but thank you for coming to our EECS Colloquium. I want to welcome you on behalf of myself and my co-chair, Eli Bronovich, right in the front. So how many people got some alert about something going on with the impeachment trial or what kind of clothing to wear today because it was raining? These are all context-aware messages that come very much from the dear and near research that Gregory, our speaker today, is Professor Gregory Abowd, really helped push the frontier on. Gregory actually was at the University of Oxford as a Rhodes Scholar, and then he spent some time at Carnegie Mellon as a postdoc, where he interacted with a lot of really sort of leaders in the field in HCI and elsewhere. And then he landed at Georgia Tech. He's been there for the past 25 years. Is that about right? Yeah, just remarkable career that he's had there. He's the Regents Professor and J.Z. Lang Chair in the School of Interactive Computing at Georgia Tech, and Associate Dean in the College of Computing. He has many titles and many leadership roles. He's also part of an ACM Fellow, and he's a member of the Chi Academy. He's really been instrumental in so many parts of at least human-computer interaction and computing at large, where he builds and interacts with real systems. You can see he brought some technologies for us to sort of experience and look at, and I think he'll show us. If you think of this idea of ubiquitous computing, that computing will be all around us, we can argue if maybe that has already arrived, or maybe it's not evenly distributed, or maybe it's here in the very wrong form that was envisioned, and I think that's part of the debate that Gregory's going to bring to us today. But he's also been instrumental in areas of context-aware computing, wearable computing. He's done a lot of work with autism and health. And the way that he does his research is also a real inspiration. So looking at a lot of the early technologies, he was able to have the Aware Home project. So this is, rather than conceptualizing what a smart home might be, they had an entire home, and that they actually a real home, and they instrumented and watched. And the same thing with work in education with the Classroom 2000 project. I'll let you guess when that work was done.
Or when it ended.
It ended, yes, correct. But he has continued to sort of challenge and reshape what computing and how we should interact with devices and technologies. Today he's going to talk to us a lot about some reframing and rethinking about those in the terms of the Internet of Materials. And so I think a lot of the focus will be on this idea of power, cost, and form factor. Join me in welcoming Professor Gregory Abowd.
Thank you, Eric, and I'm very pleased to be here. It's been a full day already. I've met with several of you here and many others and engaged in quite a few talks. And many of you, I've already given all the punchlines for my talk, so I will understand if your mind wanders. For the rest of you, I'll try to keep your attention. But here's quickly what I want to try to go over. I'm going to take a look at some past visions, one that is a local vision, came out of Berkeley in the late 90s, and the other a little earlier than that from Mark Weiser, and use that to try to critique where we are today and where we might go in the future, and to use that to try to motivate an area that I've been working on the last few years that I'll refer to as computational material. And the question is whether this actually is a breakthrough idea or basically just the next logical progression where we are heading. And I'll give you a couple of examples from the work we've been doing over the last few years. And depending on how much time we have at the end, I want to go over a number of different research opportunities, what I refer to here as the 5 Ps of research opportunities in this area of computational material. But I want to conclude with an important set of points that are really targeted towards students people early on in their career or people thinking about shifting where they might be going in their career, about ways we might think differently in the computing industry than we have in the past. So I'll start by revisiting Mark Weiser's original vision, and I would hope many of the people in this audience have read this 1991 article. If you haven't, it's the thing you should read tonight. An amazing vision that started in the late 80s and was published in 1991 of where technology might be going and how that can influence where computing research and other kinds of research should go. But it has 2 sentences. I mean, even if you're not going to read the whole thing, just read the first 2 sentences, and I've already given them to you, so I guess the reading assignment is accomplished already. But it started with the most profound technologies are those that disappear. They weave themselves into the fabric of everyday lives until they're indistinguishable from it. Now, Weiser at the time meant this metaphorically, in that these technologies would become so pervasive, so ingrained in all of our everyday activities that we would cease to recognize or identify how prominent computing is in our everyday lives. And what drove him to this conclusion was realizing that the size and shape and form factor of computing was going to have such rich variety. This is, remember, he's thinking in the late 80s when personal computing was just starting to have mainstream adoption. But he said these things are going to come in many different shapes and sizes. They will become like the electric motor, and that we probably will only recognize them when they don't work correctly, but we won't realize where computing is throughout our everyday lives. And this inspired generations of researchers. And when I went to Georgia Tech in 1994, I read this article, and it literally changed the direction of my research. And part of it was because I saw that this was a far-ranging vision, but you could start to chip away at that with some of the bleeding-edge technologies that were already becoming available. And that really energized me to move my research into much less theoretical research and more kind of experimental, empirical research. But also around that time, here at Berkeley, the work in the MOTES and the Smart Dust effort that Chris Piester and other David Culler and others tried to inspire. And so I pulled these quotes from a Mobicom 99 paper that says, Berkeley's Smart Dust product led by Professors Piester and Kahn explores the limits on size and power consumption in autonomous sensor nodes. And that size is very similar to what Weiser was talking about. Here they're talking about the fact that we'll be able to shrink down the size of reasonable computing. But the power consumption is something that really is important and what I'm going to be talking about. It says, it is certainly within the realm of possibility that future prototypes of smart dust could be small enough to remain suspended in air, buoyed by air currents, sensing and communicating for hours or days on end. That was the vision in the late 90s. Now, I had lunch with Dave Culler and Eric earlier today, and Dave actually thought that using this analogy to smart dust was one of the biggest mistakes they made. Actually, I think it was one of the strengths, because that's a very powerful vision to give to people, that computing will become as small as dust, and it will float around and will be, I mean, there's so much dust between me and you right now that we don't see. If I'd shone a light, it would become visible to us. And that was a very kind of visceral, appealing kind of analogy for an out there kind of prediction. But now, where are we today? Those are visions that are 20 to 30 years old. Where are we today? Well, today, if you think about ubiquitous computing, you see it with buzzwords like Internet of Things or edge computing. And if you look for pictures of what the Internet of Things is, you find things like that. And when I look at that kind of diagram, my first reaction is those really aren't things as I think about them. In conversation with Dave at lunch, he said, it's also the Internet of Things isn't really an internet. So he focused as a networking researcher on what it's violating in terms of being an internet, and I focused as a kind of human-centered designer about what's not thingy about that. So I'm going to focus more on the thing piece of this. When I think of things, these are things to me. And there's a big contrast between those objects and these objects. So I have two examples of an aspirational goal of the kinds of things that I would like to be able to create in the coming years. The first one starts with very simple commodity objects we have in our everyday life, like a Post-it note. And you know how much a Post-it note costs? What would be your guess about the cost of one of these Post-it notes? one way to think about this is that, if I do something like this with that Post-it note and I throw it away, no big deal, because this costs, depending where you buy it, much less than a penny per sheet. And these things are very flexible. We use them for lots of things, but they don't do anything interesting from a computational perspective. What would it mean to be able to create something like this that looks and feels like a piece of paper I can write on, but in addition to that, it has this capability that when I were to if I put it somewhere, I could essentially, like it says there, if I would tap on the little circle and then speak near it, it would record what I'm saying and transmit that somewhere. Right? A Post-it note today can't do that. But can I provide this kind of computational capability with something that is still paper-like and as cheap and disposable as a Post-it note is today? So that's one aspiration. But let's take another view of this. Let's take something that's computational today. So this is a Fitbit Flex 2. Costs about $100, probably a little less than that now. On a single charge, runs for about 2 weeks, and it can record and synthesize and analyze certain human movements and communicate that to some. So count your steps, other kinds of things, maybe calories burned or other kinds of activities. Okay? You recognize that? Anyone wearing any of these silicone rubber bracelets? No, you're not. I thought you'd raise your hand. You're not. But about 5-10 years ago, it was very popular to have these. You could have them with any color you want, with any kind of printing on it. Do you know how much, if you buy these in bulk, like 500 or 1,000 at a time, you know how much that costs? Any guesses? $1. $1. Good guess. You could get 25 of them for $1. They cost about 4 cents when you buy them in bulk, which is pretty cheap. But it doesn't do anything. They're waterproof, so you don't have to worry about where you wear them. But it doesn't do anything computational like the Fitbit Flexes. So what would it mean to be able to produce this mythical thing that I will call the infinite bit, which is something that doesn't require any charging, but can collect and analyze your movement, count your steps, for example, and communicate that to something, and still be waterproof, be cheap, and again, not require you to ever charge it. So those are two aspirational goals, going from something that's a very simple kind of a non-computational material in our everyday lives and giving it a computational capability, but still maintaining its other properties, and taking some computational things we have in our everyday lives and making them so cheap and not requiring any kind of power. So what is the gap between what we can do today and this idea of things that have computational capabilities? So why do, sorry, the last point here is, by the end of this talk, I hope to convince you that both of these aspirational goals are years off, not decades off. So a couple of years before we would be able to realize something like that, not 20, 30 years. I hope to convince you of that. But why today don't things, in my sense of the word, compute? One of the reasons is that power is a problem, and anyone who's done anything in mobile computing understands that probably the biggest design factor for creating anything wearable or mobile is how big it has to be able to hold enough power for a reasonable amount of time so that it doesn't become onerous for individuals to either plug in to recharge or to replace a battery. So power is a big constraint. Another constraint, which may be surprising to those of us who have been basically hypnotized by Moore's Law over the last 4 to 5 decades, is that computing devices are still way too costly. And what I mean by that is we cannot deploy at mass scale the kinds of objects and scenarios that I'm talking about with the cost of computing devices today. And maybe I won't get into too much detail of that, but if you want to push me on this in the discussion period, I'm happy to expound a little more about why I think computers or computational devices are still too costly. And the last thing, which kind of gets at Weiser's vision about how things might disappear, one way they might disappear is that they become indistinguishable from the other things in our life. And the problem with Internet of Things devices is that they're still too clearly identifiable as a small kind of computer. We can recognize these things because they essentially are always the same kind of integrated circuitry wrapped up in some kind of packaging, but still they don't look like the physical objects we have around us. So why I've pushed these 3 dimensions is that these are now going to be kind of the driving factors for what I consider to be interesting things to explore. And so I have these three kind of goals. One is I want to produce solutions that never require you to ever change a battery or even plug things into a wired source of power. I want things to be very cheap to produce, meaning you use simple materials and manufacturing procedures that scale better than integrated circuit manufacturing scales today. And I want them to either, from their inception, look like everyday objects, or if they're added to existing everyday objects, not to change the physical form factor or appearance of those things that they're placed on top of. So those are the driving examples. And I'm now going to try to show you some examples of these computational materials that are being driven by the power, cost, and form factor. In some cases, they fail on those dimensions, but that's the aspiration. That's what's driving me forward. And I'm going to just show two major examples here. I have plenty of other examples I can talk about, but for the sake of time, I'm just going to highlight two different projects that are different attempts to pull together those power, cost, and form factor dimensions. So the first one is in the general category of how can you produce self-sustaining sensing. And I'll talk a little bit more about what that means later on. But in this particular example, we're going to produce something. This is a project called Saturn, and there's the student, Nivedita, who's leading it, and my faculty collaborators who've been working with me on this particular project. But the idea here is that you're going to harvest power from a mechanical vibration. And I'll explain a little bit about how that happens, but you're going to do this with pretty simple materials. Plastic, paper, copper are the material, and some glue being used. And it produces a multi-layer, flexible, thin, paper-like material, but that senses mechanical vibration. Let me show you parts quickly here of a video to try to describe what's going on.
We present Saturn, a flexible, thin material that can easily be embedded on everyday objects to enable them with self-powered sound sensing and sound energy harvesting capabilities. Saturn consists of materials which are thin, flexible, and cheap. Paper and a dielectric called PTFE. The paper has a series of holes laser cut in a specific pattern. Both layers, PTFE and paper, are coated with a thin conductive layer of copper and joined together using glue dots in a grid-like pattern.
These are some of the materials.
When sound reaches Saturn embedded into an object or surface, its structure microvibrates, resulting in both layers getting in contact, generating negative charges on PTFE and positive charges on the copper-coated paper. As the layers separate,
I'll just stall it right there. Have any of you ever taken a balloon, rubbed it on your hair? What happens when you pull it away from your hair if you have longer hair than me or Eric? Right, or you take a plastic comb and you rub it through your hair, so there's a redistribution of charge. That's actually a phenomenon that many people in material science have been trying to eliminate in materials, but we're taking advantage of that. And it happens between any two materials. When they come in contact with each other, there is a redistribution of charge that when you separate them, you build up an electric potential. And the other part here is that if you provide a path to balance that electric field and keep doing the separation and contact, then you'll produce an alternating current. That's essentially what's being described here.
causing a current to flow towards PTFE. The next vibration results in the layers getting closer and in contact again, resulting in a reverse direction of current flow that completes the cycle of electricity generation.
So you take the energy from sound that creates vibration between the layers of this material, and that produces a signal that represents the variation in the sound signal itself. So you're sensing sound using sound to power it. That's why it's called a self-sustaining sensor, because the phenomenon that it's trying to sense is what it's using as its power source. That's the ideal situation. You can't always get that, but in situations where you can, here's the kind of advantage you provide from it. Let me just show you quickly the kind of quality of sound that you can produce.
This is audio recorded from Saturn.
Right, so this is a patch like this. It's actually a square patch like you've seen there. Here's something that size that's mounted on a wooden frame that's just connected in to the laptop to acquire the signal, and I just speak right to that, and that's the kind of quality you get. And I can be 6 to 10 feet away from this, and it works as a fairly good microphone. But it is just a sensor. And by that way, it's not all that interesting as just a sensor, because you got to get that information somewhere to do something interesting. So the first thing that you might be able to do is if you could somehow transmit that sensed signal somewhere where you could then compute on it, then you have at least enough to do something interesting with. So this is not something that we invented, but we leveraged in a variety of communities like mobile computing and ubiquitous computing. There have been people that have been working on ways to do passive communication. And one of the ways is by using the reflection of an RF signal, the backscatter signal, and encoding information in that backscattered signal. And so that's what this project does. On top of the original acoustic sensor called Saturn, we add this passive wireless communication. And here's a quick example of what happens there. Here we go.
Hello, hello. Audio from Zeus.
Hello, hello. Audio from Zoom.
So an unfiltered, and that's being communicated about 10 feet. But you can see we had to put in place those antenna, that RF infrastructure for that to work. Okay, so remember I showed this little aspirational goal of the post-it note that you could essentially record some audio. So I hope you're seeing the pieces there. Here is the current prototype of this Saturn patch. I'll pass this around. This is a functioning version that has two things. And it has the Saturn sensor, and then it has a single transistor that's used to modulate the impedance of a printed antenna. And in the presence of an RF field, can bounce that. And this particular one I've got has a piece of double-sided tape, so I can essentially mimic using it as a post-it note, placing it somewhere, tapping on it, and then speaking a message. Right? And this is paper-like. An actual version of this would cut out the back portion of there so that you get more vibration of the actual Saturn sensor. But this is a very paper-like material made with simple kinds of materials. It's not quite a fraction of a cent, but it's on the order of a few cents to manufacture something like this. Right, so that's the first example. So the first aspirational goal, we're not that far from being able to do. Let's move on to the next idea. So here we're going to use low-powered sensing, and specifically I want to look at printed organic materials to try to produce some way of being able to sense or do imaging around where the printed organics are located. And this is a project called Optisense. This is with a few collaborators down in the bottom left there, Bernard Kiplin and Kenneth Fuentes Hernandez, and one of my PhD students and a PhD student at Carnegie Mellon. I'm going to show you the video here that tries to get at the point of what's being done. I'm going to mute the audio because my students thought it would be really cool to have a synthesized voice read to you and then have crescendoing music. It fails as far as I'm concerned. So actually, to prove to you that it fails, I'm going to start playing it so that you'll see.
Optisense. Towards ubiquitous self-powered ambient light sensing surfaces. What if the surfaces around us can be sentient, interactive, and self-powered? We present Optisense, a self-powered ambient light sensing system. Using commodity photodetectors and photovoltaics in 0D, 1D, 2D form factors, and support a variety of applications.
Please tell me I don't sound like that when I'm speaking. But it's a little freaky, but now it gets even worse.
A surface can be represented as
you hear the music in the background?
A line and a plane. The activity sensing function of Optisense can be used to detect object states and events in 0D. In 1D, Optisense can also detect the level and type of a liquid and recognize motion patterns.
It gets worse.
In 2D, it can track multiple touch points and recognize 4 directional swipe gestures. For the rest of the video, you are going to see a data viewer at one of the corners. Data viewer consists of a
I can't mute the audio. Yes, I can.
and a recognition result view.
Ha. Okay. It's the music really annoying. So here's an idea of these are self-powered sensors, and it's just on the edge of a door. So as you open, it reveals light. So you can just detect that change in light, and you can power it. You even need less solar material to do something like that. These are all prototyped with traditional silicon photodetectors. but these are all ones where, you know, a pill bottle where you open it, you expose to light what's underneath that. This form factor is not terribly convincing right now, but I want to show you a variety of things you can do. So if I have it in a form factor like this, one-dimensional, I place it on the inside of a cup, you can detect levels, and to a limited extent, you can detect what kind of liquid is being in there because of the level of opacity or translucence of the liquid. But the next example in 1D, I think you'll understand why I'm interested. Apparently my student's not able to walk like a normal human while being videotaped. But the idea there is as you move, so this is things you can do over a 2D surface. As you walk, your body naturally blocks light coming from this side, and so an array of photodiodes on your wrist will essentially show a pattern that is indicative of your movement, so you can count steps quite reliably with relatively simple algorithms to get at that. And then a two-dimensional form factor allows you a surface to do interaction like multi-touch and hovering kinds of gestures, and that's what's shown there. So this is getting toward this idea of the infinite bit that I was talking about earlier. So these are the three different kinds of form factors that were shown in the video. A single point pixel, a 1D array, and this is a slightly different version there than what I've got here, but I can pass this around. By the way, even though I'm talking about these things being cheap and interesting form factor, I do want the props that I sent out to come back somehow. Who hasn't started? You in the back haven't started with something. I'll get the one here. Thank you. I love walking around while I'm talking. Thanks. Hand in all of your props. You can use this 0D, 1D, or 2D arrangement to provide a number of different ways, and we prototyped here using these traditional silicon photodiodes. So here's probably the slimmest form factor of that, but if you feel that it's rather bumpy, right, I wouldn't say that's entirely flexible, but with printed organic electronics, you can produce that same thing with a form factor like this. It's very thin and flexible. You will confirm that that is thin, sir?
Yes, it is.
It is. Would you confirm that this is flexible?
Oh, so flexible.
Thank you. Thank you. Checks in the mail. Now, the reason why I don't demonstrate this is because the manufacturing process for these, though it is scalable and cheap, it's not terribly reliable. So these different photodiodes actually have different performance characteristics, which screws up the circuit when you're trying to do some kind of sensing. We're working with them on ways to produce this through a single printing procedure, but this is where we're trying to head. And if you've got something like this, then you can imagine the form factor of the one-dimensional form factor that I passed out there, and I don't think I have the single dimensional one, would be a little more appealing in terms of its overall form factor, and much cheaper to manufacture these kind of printed organics than it is to produce these silicon integrated circuit photodiodes. Okay, so those are two examples of computational materials. And I see I've got maybe about 10 or 15 more minutes before we then go on to some conversation. What I want to do is talk about some research opportunities in this space of computational materials. So I hope I've tried to motivate here by saying if we look to the past visions, we're not quite where those visions said, and I see Chris in the back there, and I pointed one of your quotes from your Mobicom 99 paper about smart desk and Weiser's vision. I said, those were great visions. We're not quite there, but here is a very reusable philosophy for the rest of your research career. Every once in a while, read a paper from 20 to 30 years back and reinterpret that paper in the context of today. That's literally what I've done to try to motivate this computational materials work. This is a way to essentially keep your research moving forward. Just use other people's ideas and reinterpret it, because something interesting will almost always come of that. And there are very few real new visions in this world. And I'm not presenting a new vision. I'm presenting a new way to achieve an already existing vision. That's one way you could interpret here. And I showed you two examples of how we are moving in that particular direction through this example of a thin multilayer material that harvests energy from a vibrational source, uses passive reflective wireless communication to essentially produce something that's paper-like that does something computational, and then a way of being able to produce form factors that can be 0D, 1D, 2D that do something interesting, but run at such low power they can be sustained by already existing solar harvesting technologies in ambient indoor lighting conditions. Okay, so that should say, all right, he's not talking a whole bunch of crap. But now what's the long-term research agenda here? So I think there are 5 different topics that are interesting research opportunities, or at least 4 of them are research opportunities, and one of them is a way of conducting research. So, and I'll try to spend a little time on these, but not too much. I can talk later if people are interested. So one of the challenges is how do you produce these power-savvy platforms? The next is how do you prototype relevant user experiences? Do you see the trend? The next is what are the production practices that have to change in order to be able to produce these large-scale, low-cost, self-harvesting or self-sustained things that have the right kind of form factor? What principles should you keep in mind to both drive innovation but also balance or check, prevent the kinds of innovations that might be dangerous? And finally, what kind of people do you want to work with that provide you the right kind of disciplinary input to support this kind of innovation? What knowledge matters? So quickly on the power harvesting, I showed you an example of a self-sustainable sensor in this Saturn vibration harvesting one. But that's a general idea I was talking about. So what are other examples of being able to use self-sustaining sensing situations? Well, one of them, do I have the video here? Yeah. Here's another one that was recently presented. This is a very quick video I'll just talk over.
We introduced Serpentine,
yeah,
a self-powered, diversibly deployable.
So this is essentially a silicone cord that has some conductive threads woven inside it, and this, as you manipulate it, it generates energy, and the energy signal that it produces is emblematic of the actual way it was manipulated. So I can detect a pinch because it looks different than a pull or a twist. And here are some examples of different ways you might incorporate that kind of self-sustained sensor in a variety of different situations. So that's an example of using physical manipulation as the energy source that you want to then be able to classify or detect. You can do the same thing with water. Here's an old prototype of creating multi-layer materials that are essentially use water as an electrolyte between a cathode and an anode material, and it's mostly thin and flexible, made of non-toxic materials. In the presence of water, generates a lot of energy that you can use to essentially communicate, hey, there's a leak here. Right? So that's another example of a self-sustainable sensor. But what are other kinds of phenomenon that you can sense by using that phenomenon to power the sensor? So think about that notion of self-sustainable sensing. Another one I quickly want to talk about, I mentioned this idea of using passive RF backscatter to do wireless communication, but the problem with the one I showed with this Zeus one was that we had to put the RF infrastructure relatively close to the patch for it to work. In this particular project called Ubiquitous, and I won't show the video here, we're leveraging ambient FM signals. So the downside of an FM signal is you need a fairly large antenna to be able to receive it, but there are a variety of situations in which you have that amount of space. For example, on my body, within my clothes, I have enough length to be able to produce the right kind of a signal. It's also not as clean a backscatter as some other frequency levels are, but if I could just get it to backscatter reliably about 1 meter to 1.5 meters, that's roughly the distance between my finger and a smartphone. Smartphone, at least Android ones, have an exposed FM receiver. So I now have the ability to do passive wireless communication to a device that can then send it anywhere I want. So the real innovation here is that we do a much more practical form of backscatter to give you truly ubiquitous interactive surfaces. And I'll maybe show you some quick examples of that next. So that's power. I have a lot more to say about the power side of things, but I want to move on to at least one more challenge area, and that's how do you prototype user experiences. So as Weiser himself said, applications, to paraphrase, are the whole reason you explore technological innovations. Compelling applications are the whole reason why people put money into purchasing things and to investing in infrastructure to make things possible. There has to be a compelling human need. You cannot avoid that. At least myself as a computer scientist, not particularly good at coming up with the most compelling applications. So usually the best we can do is show that there are a wide variety of potential applications, and someone out there is going to figure out the one that really matters. I'll give you a little bit of a hint. I think this self-sustaining water sensor that detects leaks inside building materials is a possible winner. But that's for the construction industry. Would a wrist-mounted device that always that never needs to be charged, that can count your steps, is that really a very compelling application? I'm not so sure. So the question is, do we have compelling applications of computational materials? Well, I started the talk with 2 examples, and I don't expect you to believe that those are the most compelling ones. What I wanted to show you is that these are at least some aspirational goals, and we're not that far from being able to do things like this. But are you going to run out now to Office Depot and buy computational Post-it notes? I don't know. Are you going to run out right now and invest in, was it Google that bought Fitbit? You know, the Infinite Bit was a little bit of a play on Fitbit, and you know, maybe they'll purchase that idea for me. I don't know if those are necessarily the most compelling applications, but those are at least end-user facing applications. But what are some other things we might think about? Well, that Infinite Bit is in the area of health monitoring. So there's lots of work that's been done trying to leverage smartphones as commodity available sensors to do clinically relevant health sensing. Okay, so we do this because everyone has a smartphone. Well, my smartphone died on me 2 days ago, and I have this replacement that I had around my house, an iPhone 5, which you can think of the iPhone 5 today as just a convenient paperweight, because there's not much I can do on this because it won't run most of the applications that I rely on. So this is just, I can use this to communicate into text. And 20 years ago, that would have been wonderful to have thought I'd have something like that. Today, this is a crutch. Just being able to communicate to people by texting and by voice. But let's think from a computational materials perspective in health. What would happen if surfaces could do the same kind of sensing that these commodity smartphones or wearable devices could do? What would it mean if walls and tables and clothes could detect coughs and determine the spread of flu? Or be able to determine other kinds of relevant physiological characteristics? Well, the reason we don't do that today is because it's too expensive to produce these kinds of materials at scale that you could put on any chair or any table. Some other uses, I showed you vibrational mechanical sensing. Here's an example of an array of those patches showing that you could alternate which ones are used for harvesting purposes, which ones are used for sensing purposes, and how can you improve the balance between power to do other things and making it a good auditory or mechanical sensor. So you can do this in large scale, so make that like wallpaper, so you now have wall surfaces that are high fidelity acoustic sensors. You could place these vibration sensors on heavy machinery to be able to monitor the vibration to determine in advance when things start to wear out because they have a different signature of their vibration. You can put the same kind of technology, it's fairly durable, under carpets to be able to determine when someone's stepped on something that produces enough of an impulse that you could then communicate that there was a step there. We might be able to do this at such a fine level that writing, which is actually a mechanical vibration across the surface, could also be detected. So these are things that we might do. And these are the kinds of ideas you get from a technologist like myself. But what's really interesting is I now work with some industrial designers, and I know there's some design influenced people here, and when you show them something like this, their immediate reaction is, oh my gosh, that's like paper, like the craft material that is what we use in our everyday design activity. So when you show something like this to a designer, here's what they come up with. I look at that and I go, so what? They look at that and say, oh, that's great. I made this, this piece of art, and the elephant's ears are now empowered or enabled to be able to sense because I used your material on the ear part. And they said, that's really compelling to open up to designers, be able to use these kinds of materials in this way, and for them to do more than just look interesting. Right? Let's think about the imaging surface idea that I gave you. So what if you could make any surface be able to image or be aware of activity around it? Right? So I talked about that ubiquitous that leveraged the FM backscatter to make it truly kind of ubiquitous as long as it's kind of within arm's reach and could backscatter to a phone that I have in my pocket. Well, here are some ideas of what you might be able to do. You could embed it in clothing, which is up on the upper left-hand corner. Down here are posters, and these posters are interactive. I can slide across here and communicate that that's the one I'm interested in finding out more information, and can communicate that to me and then get the information off the web. I can use this as a kind of voting mechanism. I can slide here to vote for one of these particular individuals. One that's particularly compelling to me, Eric mentioned that I do a lot of work in the autism domain. That's because I have 2 boys on the spectrum. And my oldest boy, who's now not a boy, he's a young man, he's 22 years old, cannot speak. And he's learned over the last few years to be able to communicate by typing on a laminated board, something that looks a little bigger than that has the letters of the alphabet he taps on here. right? And so I hold this as his communication partner. He taps on there, and then I have to scribe down what he's written. So how can I turn something as light and flexible as this into a wireless keyboard? Well, here's a working example we have here that leverages the fact that the printed antenna on the back there, when you hold it as a human, you now become the antenna that reflects information a particular direction. So I can now detect when you tap on these particular numeric keypads to be able to wirelessly transmit with something that is like a piece of paper. Right, so there's a couple of examples. Here's something that extends the idea of Optisense that I showed before. All the kinds of interactions I showed here were used with an array of these photodiodes that could ultimately be replaced by these printed organics. This is the value of working with people from different disciplines. Once we showed this, and particularly that band, where is that band? The one-dimensional band that's there? Yeah, that back there. We showed that to our colleague, Kanek, and talked about this idea that when you walk, you essentially get these differing patterns on the different diodes. He said, well, you could do that with a single diode, because if you have a particular shape to a printed organic diode, and you continuously measure the voltage reading, you'll get the same kind of information by passing your finger or changing a light source over it. Let me show you quickly what this idea means. What I've got in the back here is that's a traditional photovoltaic. But any kind of photovoltaic can also operate as a reasonably good photodiode. So it's essentially playing the role of a printed photodiode for me. And on top of it is a mask that gives a pattern of what part of the photodiode is exposed. As you move your finger one direction or the other, you'll get a different pattern that will indicate to you which direction you're moving. So maybe you can't see it very well, but trust me, as I move in this direction versus that direction, I get a different looking image of the voltage pattern measured over time. And that's done with a single sensor. And the advantage of these printed organics is that it's easy to produce these with arbitrary shapes. It's very difficult to do that with traditional silicon integrated circuit photodiodes. We have a way of being able to mimic these arbitrary shapes with the silicon photodiodes for our research purposes, but ultimately what I'd like to be able to do is to print something like a barcode that not only communicates the motion, the relative motion of things above it or its movement relative to an otherwise stationary environment, but also to communicate information like an ID. So imagine a barcode that can be printed onto objects that now can communicate information about the object that's connected to it. I'm going to stop there and talk to you revisit that there are 3 other research challenges I haven't talked to you about, and I'm happy to talk at length about those different research practices. But I want to conclude here with some attempt to be inspirational in terms of how you need to think differently to play in this kind of space. So the visions from Mark Weiser and from the Smart Dust effort, to me, suggest a future that looks more like this. Everyday materials having some computational capabilities. Now, what's really influenced those of us who try to be creative with computing technologies is Moore's Law. And it's been great for decades and decades, and I don't even want to argue whether Moore's Law will continue or not. That's not the relevant point I want to talk about. What I want to talk about is this notion that computers will always get smaller, cheaper, and more powerful really influences how we think as creative individuals about computing. What we do, and we see plenty of examples of, here is portable computing, and here's portable computing 25 years later. You can do this with a number of different domains. And you see that for the same amount of dollars, you get something that's more powerful, that's slimmer, sexier, more functional. And this has happened in a number of different domains. So as researchers, what we do is we build an initial prototype of something like, say, augmented reality in the late 90s. Someone's carrying a big backpack with multiple computers, a GPS antenna sticking out of their head, and these really poor goggles that do a monochrome image overlaid on top of what you see through those goggles. And someone says, that's enough. That is the image, the research contribution of augmented reality. Moore's Law is going to take care of the rest of it. Going to make it run in real time and be packaged much smaller. You as researchers don't have to do anything, and just the passage of time will turn that into something that will be a more appealing version of augmented reality. And I would argue that that limits how creative we are with the technology. We always think about things shrinking, 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 and become faster and more powerful and not costing that much more. I would like you to think, so the project that we have at Georgia Tech is called Cosmos. And so what I at sometimes refer to as the Cosmos conjecture, but I'll now talk about it in terms of Cosmos thinking, is that these computational materials, and here are ones that I've shown you we're not too far away from. Way we should think about this is as time progresses, we're going to be able to produce these things at larger scale, so driving down the cost of them, so they'll be cheaper, and they're going to be more functional. They're going to do more and more things, but they're going to be easy to deploy at larger scale. And that's a really different way and a way I want to get people to start to think. And the reason this is happening is because in Moore's Law, the emphasis, this is the actual original wording of Moore's Law, and my emphasis here is that increasingly clever ways to manufacture integrated circuits. And I think we need to challenge whether the only way to create interesting computational things is through integrated manufacturing techniques. It's not the only way to build things in this world. And it has its advantages and its disadvantages. So I would say my version of Moore's Law that's focusing on computational materials is that you're going to use increasingly clever ways to manufacture at lower cost and larger production rates to produce more and more interesting applications and computational materials. And I don't know exactly who this quote came from, but quite the visionary. So there's a variety of things that are missing in what I've described, but the last point I want to draw on here is the number of people that have influenced the things that I've shown you here today. And the emphasis is more on the right-hand side, the different disciplines that have been involved. And the ones that are not ones that computer scientists typically interact with, the top two. You typically don't interact with material scientists as a computer scientist. You certainly don't interact with many chemical engineers. And I hope to motivate in you the need for us to understand more about the base materials and how they're manufactured for us to be able to produce these kind of large-scale, cheap, easily deployed computational materials. So my message to students is you should strive to be influenced by all of these disciplines if you want to play in this particular space. First of all, if you're motivated by this message of computational materials, that's great. If you want to do something with respect to that, then you need to be influenced by a variety of different disciplines that you may not be influenced by today. So I'll point to you, acknowledge a number of the students that have been involved in a lot of this work, and I'll thank you for your attention. And I've left a few moments for us to have a little bit of a discussion. Thanks.
Great. So we do have time for questions. This is our crazy question box. You hold it up like this and you can talk and ask questions. Do we have questions? I know we do. Great.
I wanted to catch the crazy box.
So William Gibson, the sci-fi author, was asked in an interview once how he had such foresight into how people were going to be using these cutting-edge technologies. And he said that he didn't talk to technologists because technologists had no idea how their stuff was going to be used. He said, "Give me a room full of artists and criminals and I've made my lunch." So you went and talked to artists. Have you talked to criminals about these technologies?
Well, how do you know I'm not myself a criminal? But you bring up an important point, and that's one of the P's that I talked about there. The principles that we use and understand that influence what drive our innovation and may check the innovation. So we can't always predict the good or bad emergent properties of the things that we provide. But one of the potentially sinister things that I am suggesting is a future world in which it will literally be impossible to disconnect ourselves as physical beings from the digital universe because the surfaces around us will all be computationally enabled. And that in and of itself is scary. Right? So what should one use to essentially check those kinds of capabilities? So let's go back to this particular Post-it note idea. So in the image that I showed you, it said, tap on this to record. Okay, one of the advantages of something like this is it's got a physical manifestation, and you have to be relatively close to this for the microphone to work. But you don't necessarily know that. If this is sitting here, how do you know way in the back there that I'm not recording what you're saying? You don't know that. Right? So one way we can address this is the only way this is activated is if by touching it you essentially complete enough of the circuitry so that it can be functional. So I now make this something that requires my active participation in order to be able to make it functional. But why would you believe that that's what's needed? There's no feedback that this provides to let you know that it's recording. So one of the ideas that we have, which I don't think is very far off, is that in addition to my pressing on here, that's producing enough energy to essentially light up a recording indicator, or extra energy that's beyond what's needed to do the sensing here is used to power some feedback literally on here using something like very low power electrochromic ink that would indicate you it's recording only when it's blinking. But that still doesn't address the problem, because the whole problem with these kinds of sensing technologies, what do people believe is the use of something. So I can tell someone, oh, there's a camera up there, but it's not recording right now, and probably 9 out of 10 of you wouldn't believe that. Right? That's why you see people put tape over the camera on their laptop, because that's a physical block to being able to do that. Well, when something is a piece of paper like this and I don't want it to be recording, what can I do? Right? And if it's cost less than a penny to do that, I, as the one who wants the microphone, not so bothered by something like that. But that's a long-winded way of saying I don't know all the emergent negative problems with these technologies I'm talking about, just like I don't know all the emergent positive values. But I'm a responsible technologist. I can't ignore the fact that there are some privacy implications. But there are other principles that matter. How do I source the right materials so that it's a renewable source that's used to produce these things? How do I make them disposable so that when I do this ripping up and I throw it away, that I'm not adding more to the collection of e-waste in the world? When you have complete control over the materials you're using, you can choose materials that have more than just interesting computational properties. They can have other properties as well. If you don't get down to the material level, then you're at the mercy of those who produce the hardware. Yes?
Hi, Gregory. I've got 2 questions. The first
You said you were going to leave, Flora.
I should stay back, so it's nice talk. So the first one is, what about the material properties themselves? So a lot of material scientists have looked at actually using the material properties themselves to actually transfer bits. So have you been exploring different modalities, not just paper? And the second question is, in the world of cyber-physical systems, one of the most important aspects is the actuators. So there's a lot of research into the sensing. What about the actuators?
Yeah.
What will be the future of actuators, and what does it look like? Does it still look like what we have these days?
So your first question was about, I had a quick answer. What was the first question again?
The properties of the materials themselves. In terms of materials, the materials themselves, as in terms of property. Let's say graphene.
Yeah. Okay. So you said to do more, to do other things other than just sense things.
I mean, there are things like,
Yeah.
for example, the graphene inks to
Sure.
sense lights.
My quick answer to your question is that no, I have not myself explored those things. What I'm trying to do is to say there are all these things that we can explore if we want to collaborate with or understand better material properties, and particularly storage and actuation that you mentioned are things that we haven't explored too much. But anything that's computational senses, it communicates, it actuates, it stores, it communicates, and you could say it does some kind of computation. And we can look to properties of materials to do all of these things. All I've really focused on is sensing and communication, and doing it in a way that respects these kind of cost, form factor, and power parameters. But there are plenty of other things to start to explore. I mentioned just a little bit about an actuation in the form of visual display that has some value. I didn't talk about any kind of mechanical actuation, but a lot of people that work in 4D printing, using metamaterials that use water or heat or electricity, are looking at those kind of actuation capabilities. But they're not looking at it from the perspective of self-sustainability, from a power perspective. Great demonstrations, but they almost always require some external power source that's not going to scale. So we need to start looking at those things. But you're absolutely right. There's a huge agenda of topics to explore here.
Thanks, Gregory. Seems like you focus on scale and low price requires that we understand things about economies of scale and mass manufacturing, and what kind of processes are particularly amenable to becoming really cheap, which is very different from can we 3D print something where every object is different, but every object costs the same. This is really getting us to think about, as we produce more, where does the price really bottom out? And so what processes do you have in mind that are really promising here? Is it in textiles? Is it in paper mills? Is it in, and that also is kind of a daunting task to understand that whole world.
Well, certainly for a computer scientist to think about, but I'm going to point you out to my colleague here. Can you see that? Mike Filler, who's a chemical engineer. And he's really influenced my way of thinking about this. And he's the one who points out that the real advantages and advances we've made in integrated circuit manufacturing is how masterful we've become in the hardware industry of doing better and better integrated manufacturing techniques. But for those of you, I'm probably telling you something you already know, but I'll iterate it anyway, or reiterate, that the issue with integrated manufacturing is that the yield rate you get after X number of steps of an integrated manufacturing is compounds at each step. So even having like a 99.9% yield rate, meaning 999 out of 1,000 devices you develop are good. You only have to throw out one out of those thousands. Even if you have that level of yield, which is really hard to get to, you do 1,000 steps of manufacturing, and typical integrated manufacturing in the IC industry today has easily 1,000 steps. You get below 90% yield rate very quickly. Right? So integrated manufacturing has this already daunting task of having to be perfect at every step in order to have reasonable yield rates. But other things that are manufactured in the chemical industry, think gasoline, think chemical molecules, they're done in a completely different fashion. There is some chemical process that produces a huge number of these kinds of elements, but they have all different kinds of characteristics. There's a separate phase that factors out the ones that have the properties that you consider to be of value. And usually, in a good, efficient process, you're going to use all those different fractionated components for different kinds of applications. So imagine being able to bulk process a transistor, billions at a time, but they all have different performing characteristics. And then imagine a second step that it can essentially factor out the ones that have the certain kinds of performance characteristics you want and produce, a bowl of these, a mole of these transistors that you can put into solution and have as a device ink that you could then, and you have some guarantee of their performance levels. That's a different way of thinking about manufacturing computing devices. You then could disperse those inks on a surface and then use a computer-guided, a vision-guided system to essentially wire them in the way you want. And every time you wire them up, they could have a different kind of wiring to give a different kind of capability. So that's a different way of thinking about manufacturing computing devices. And let me tell you, I don't think we're more than a decade away from that being possible. Right? So these are not really far out visions. What can we do with that kind of capability?
So, really fascinating talk. Thanks for kind of the mind-bending aspect of it. Your question was paradigm shift at the end. Mm-hmm. And I think it may be a paradigm shift, but I think not in the way that you're asking, which is that it's a paradigm shift for society. And the question I thought Megan was going to ask had to do with affordance discovery. Even with the relatively few IoT devices that we have today, affordance discovery is very difficult. So when everything is computational, how on earth are people going to figure out what they can interact with and how without instructions everywhere? And that is a paradigm shift for the individual or for society. How are we going to jump across that bridge?
I think if it works, it'll be gradual and then it'll be an avalanche, right? So I don't think it takes too much effort if you can read this handwriting to say, okay, if I can follow those instructions, all I need to do is speak to that particular note, right? You're not at all used to thinking of a Post-it note as being a microphone, okay? So what you're saying is, when would I believe? So one question you had was, I fear that being a microphone. Your question is, do I believe that's a microphone? Right, so how do I prove? Yeah, well, how do you know? Here, I've told you, right? Now, do you believe it? So how many people think that's just a joke? In the example of the infinite bit, you believe it if you could then essentially pull out your phone and see your steps being counted, right? And take it off and your steps aren't being counted. So there's the belief, and I already know what activity trackers do. You might go back to some of these other examples I showed, right? So why would I think when I see a poster that it's interactive if it just looks like it's printed? It's printed on top of a series of conducted traces underneath there, like that are kind of exposed here, but they're hidden by there. How do I know that when I touch that it will behave like a wireless keyboard? Well, the fact of the matter is that there's already a collection of people that use this as a way to have an individual tap and then they write down. So have a laptop near it, and as I tap on the 8, seeing the number 8 show up, says, oh, well, that's interesting. That's actually reliably, when I tap on that letter there, I get it over here. So it's the kind of thing that you might not think when you see that tapping on it's going to wirelessly communicate. But once you see it, then you understand what's going on. I think you need to provide some kind of instantaneous feedback in these scenarios, and we talked a little bit about this today. I want to generate some energy from the notion of being able to swipe across here. It says swipe on the event to receive an invite, right? So I want to swipe here, and that's going to cause, in the technology we got, that will cause the information being transmitted to your phone and then things happening from there. But how do I know that's happened? Well, I could make my phone vibrate, but how do I know that's not just some other notification? But if the act of swiping here causes that last arrow to kind of blink when I've done it, then you have some kind of feedback that I've done something in the physical world that resulted in some action happening. And this is why I think it's going to take a little bit of time and some cleverly chosen initial applications, compelling applications for people to want to do that. And then once people see this happening, then I think there'll be an avalanche of these kinds of capabilities. I could be wrong.
We have another question in the back here.
Yeah.
I have a question, but relevant to what your previous question. We already have the problem that in New York City they had a bunch of buttons you pushed to say I would like to cross the street, and the city just made a lot of them placebos, and they just didn't do that. So I don't know.
That's a trust element.
Yeah, it's an interesting problem that we already have. My question is something I've been concerned about for a long time since I heard of smart dust 20 years ago, or I'm not quite sure when it started occurring to me. But there's a lot of people saying that we have nano engineering now, which is sort of like fancy chemistry, really. But we're also just burning things and producing nanoscale particles, and these seem to be really toxic. You breathe them in, get into your bloodstream. They seem to be really toxic to humans. And we're talking about, hey, let's take all this computing and just put it in the fluids, and we're going to be drinking it, we're going to be breathing it. This sounds like a really bad idea. You're talking to people on like what scale. If something's big enough you can't swallow it, you can't breathe it. Something's tiny enough, it might not bother you if it's water molecules. But what are the scales where it is toxic and it is going to get in?
Yeah, so I think that the piece that you're kind of objecting to is this part that says they'll remain suspended in air buoyed by air currents, right? And that's an interesting kind of vision. What I've been showing you are not things that are kind of free flow. They're kind of on established surfaces. But there's still no guarantee that the electronics on here don't somehow kind of migrate out. I'll take the example of the multi-layer water detecting material, which was intentionally made with non-toxic materials. So non-toxic, but also has a shelf life of decades, because the idea is this becomes something like Tyvek. So it sits as a layer in between other construction layers and only gets activated if water unfortunately seeps through from one side and then communicates out. And then effectively it wears out. But that's okay, because if water leaks in there, you're going to want to repair. You're just going to want to know where to do the repair. But my larger point is that's why I say it's important that we become very more knowledgeable about the base materials that are used for these computational devices, because then we can ask the questions and limit our exploration to materials that have the properties that we care about. So non-toxic, can be manufactured from renewable sources, can be decomposed or are biodegradable.
So you have great experience in this field. Scavenging energy is important. So we have sound waves, we have room lights and other forms of light. We have radio waves like Wi-Fi. So what is the best form of energy scavenging?
So the best form of energy is the energy you have where you want the computation to occur. So there's a whole piece of this talk I didn't do today that I have a PhD student on who's taking the automobile as the environment to explore. And the question he's asking is, where would you want to put sensing capabilities on a car? And what are your opportunities for harvesting enough energy at that particular location? So, for example, a car that has an internal combustion engine produces a lot of heat. So a thermocouple or thermoelectric harvesting is something that's interesting. But where on the car do you find appropriate temperature differential? And is that in a place close to where you'd want some interesting computation? Well, one example is the exhaust pipe, pretty hot. The exhaust pipe is in the rear of the car. So rear sensing solutions attached to the exhaust pipe are ones where you can harvest enough energy to essentially power a retrofitted rear sensing capability. So it's not about what's the one single harvesting technique that's most promising. It's where's this match between what you can harvest close enough to where you want to do some form of computation. That, I think, is the interesting question to try to explore.
All right. Okay, I think we're going to wrap up.
Okay,
But I actually want to get a recommendation for you. So you mentioned about reading literature from the past 10 or 20 years and being inspired and kind of revisiting that throughout your career. And I think you also hit on this interest of very different disciplines being part of the conversation and part of the innovation. So is there a reading list for the future that's maybe other disciplines outside of engineering that we should certainly be paying attention to, if it's science fiction or is it like other
definitely science fiction, because they usually explore the implications of technology because they can just assume it works and they don't have to make it. They can produce an imaginary world. So definitely science fiction. But to answer the other, probably more interesting point, ask me that the end of March, because I will have just completed my first example of a 5-week mini course with my collaborators in chemical engineering and material science and electrical engineering on an introduction to computational materials. And I think in the process of that, I have some compelling videos, particularly on the engineering side, about what's really complicated about integrated manufacturing and what's not as complicated about other forms of manufacturing. I think that's a compelling story to tell people. I also have some interesting papers about how you can grow a PN junction through chemical, nanochemical growth techniques, which I think is very inspiring, but I don't have the complete list right now.
All right, reading list coming in the future. Thank you. Let's all thank Professor Gregory Abowd. He will be around for a little bit. Please, you come up, and if we didn't get your question, that's fine. I will have to steal them away at some point, but there's a little bit of time, and you can check out the demos here. And please only tear the real Post-it notes. Don't tear the demos.